Okay. So for number 16, okay, not forgetting what we covered yesterday, which was the URMS with the square root of 3r over molecular mass, or molecular weight. Make sure we're using the 8.31 constant for the joules, and make sure all your masses are in kilograms. And then we also had the equation yesterday where you put your molar masses in a ratio with the different rates as well, and they're kind of opposites and squared. So make sure you watch the end of the video if you didn't do that yet. For number 16, it says consider the 3 identical flasks filled with different gases. You have flask A with carbon monoxide, flask B with nitrogen, and flask C with hydrogen. As you can see, they all have different pressures, but they are at the same temperature. What is 0 degrees Celsius in Kelvin? 270. Right. All right, so we are all at the same temperature, which means they all should have the same what? Temperature is a measurement or proportional to your kinetic energy, right? So this first question, when it says, which flask will the molecules have the greatest kinetic energy, what's that answer? They all have the same, right? So this is a trick question, okay? Because kinetic energy is proportional to that temperature. The thing that's going to be different is their different masses will cause them to go at different rates or different speeds. So it says, in which flask will the molecules have the greatest root mean square velocity? So that's where we have that little URMS thingy, okay? And so looking there, if we know that this is our base formula here, okay, that means that they all have the same temperature, they all have the same constant, so this part goes away, if you think about it, right? So really, it's based off of their molecular weight being related to that velocity there. Okay, so if it's at the bottom of a fraction, what does that tell you? As molecular weight goes up, what is... Right, velocity is going to go down, okay? There you go, okay? And so knowing that, you can just kind of look at them. We know that the mass of carbon monoxide, if we were to look on our periodic table, is going to be about 28. Nitrogen gas is going to be about 28, and then your hydrogen obviously is going to be 2. So looking at those, who will have the greatest velocity? Hydrogen, exactly. So hydrogen is the winner there due to that low molecular mass or molecular weight. Sorry.
And the pressure doesn't matter.
Not for this. Nope. Nope. Because if you think about it, the pressure is coming from them moving as fast as they are and hitting the sides. Yep. Okay, so this last little part that we're going to look at for the non-ideal gases, all that you really have to know is that this exists. You won't be asked to calculate this except on little labs in like college and things like that. So we're not going to do any in here though, probably until the end of the year. So just so you've got it, underline the couple things that I'm going to underline, which is the volume occupied by a real gas is not negligible, as suggested by the second postulate that we read the other day, okay? Because a gas particle actually does occupy space, okay? And the higher the pressure, the more gas molecules are present, and the more significant their volume becomes, okay? So high pressure, okay? So basically, remember your ideal stuff is at low pressure, high temperature. Now, if we have the high pressure, now things become more real, basically, okay? So gas particles of real gases do experience your attractive forces as well. So the slower that a gas molecule is moving, the more chance it has of experiencing that. So what do you think that's going to be related to? If this one's related to high pressure, what do you guys think this one is talking about? Temperature, right? So if we have lower temperature, everything slows down. Again, things become more real. So thus, a real gas deviates from your ideal gas behavior at high pressure and low temperature, okay? We'll have an equation that corrects that, and that's called your van der Waals equation. Okay, so this is just kind of one to kind of just know is in your notes, okay? But looking here, what this is telling you below it is that this little part right here accounts for pressure being added, okay, because we're increasing that amount. And then for the volume minus this, we're saying that it's not all empty space anymore. Okay, so we're accounting for that little bit there. And that's what they're talking about for this. So the question that they have for number 17 says, explain in terms of the van der Waals equation why hydrogen chloride is much less ideal than hydrogen gas. Okay, so very quickly, volume, okay, HCl, thinking about those two things, who's bigger, hydrogen gas or HCl? HCl, yeah, HCl is bigger and takes up more space. Okay, and therefore you need to add in that extra little bit for the volume being accounted for, okay, or taking away from it, sorry. And then finally for your pressure, polar molecule means that pressure is higher. I'm sorry, pressure is smaller. Ooh, sorry, my bad. And that's just because if it's polar, that means that it's attracting more to itself than it is to the sides of the container, okay? So pressure is smaller, so you need your correction factor on that one. Just taking a little more of your time, I'm just gonna also tell you about for the pressure thing, it becomes important also when you are dealing with something like H2 versus your I2. And this is the next unit you guys are going to go back into is your intermolecular forces. If you remember for the polarizability idea, H2 is very small, right, in terms of how many electrons are floating around. When you have I2, remember it's kind of like that, right? And so you have all your little electrons there. When they hit the sides of the container, what happens to all those electrons? They all go to like one side, right? And so now we actually have a partially negative, partially positive side. So your bigger molecules are going to have that more pressure. That's all that I wanted to say, and that's what I'm saying.